Hello, we're going to try a problem from chapter 16 of Halliday, Resnick, and Walker, particularly on wave functions, as you can see here. And we'll use the wave equation that involves second partial derivatives in order to do that. Now, this problem may look a little bit intimidating, but it's actually not that hard, and let me show you how. I'm just going to go ahead and just highlight what we're given, and pretty much this is it. That is all we're given. And using the wave equation, use a different color, which kind of tells us what to do. We do that first, second, and then you can solve for that third. Boom, look at that. Just to remind you what the wave function looks like, it is y t equals, and this would be the amplitude. I like using a for some reason. That is kx minus omega t plus r phase constant. So from here you can see that's not a 4, okay. Which number results to which? Okay? Cool. So I'm actually going to go ahead and follow my steps right here. Let me just erase that. And go ahead and take some partial derivatives. So given our function, I'm going to start with this. Now, take note that when you're taking the partial derivative with respect to a certain variable, in this case x, that only the x parts are the ones that are differentiable. Anything else will become a constant, and the derivative of a constant would be 0. Okay, so I can actually basically ignore that. Makes things kind of simple, actually. And the derivative of a sine function is a cosine, and you just copy what's on the inside. But now I have the derivative of the function inside, and that's honestly just going to be 1.2. Oh, that's it. And one of my students showed me you don't have to actually multiply it yet. Since these are just constants, you just lay back and write it all down. Okay, because our next step would be to take the second derivative with respect to x. Okay, and so this is still going to be 4.3, but now it's minus sine, use a bracket there, then once again multiply by what derivative of what's inside the argument of the trig function, and that just results into 1.2, because remember, these basically are constant with respect to x. Okay, and so the second derivative turns out to be, just for that first part, okay, is 4.3, the amplitude, times squared, and it's actually back to sine, and it's negative. And just copy that argument right there. I think I'm going to go to the next page. And so this is d squared y. Okay, so I'm going to hold that thought. And now let's I'll just use black for this one. Derive my function, my wave function, now with respect to t. So going back here, now only this part will be differentiable, and these two will just be constant, and derived in respect to time would just be 0. Kind of make things easy. Okay? And it's still going to be derivative of sine at first is going to be cosine, and just copy. But now multiply by the only differentiable part, this, and it's going to be a negative 4.7. Okay? And so that's going to be negative 4.3.7 cosine of all of that. Okay, and then take the derivative again. So it's a repetitive process, and actually it can be a bit tedious, but this is not too bad. Now this is a minus sign. Times a negative 4.7. Boom. And so the second derivative ends up being still a negative. And I'm just going to gather all the 4.7s up front, and you'll see why we didn't multiply it. Just 4.7 squared times sine it's pi. And there we go. Okay, so we're going to use this. I probably can't barely see the yellow. And this to solve for our original wave equation. I'm going to go back to blue. Okay? So going back to this equation here, it kind of highlights it as well. And I'm just going to copy that down here. Oops. Zoom out. Zoom in. Go to 1 over v squared, and we're solving for v. If we're solving for v, and just expecto chango, and then that's going to give me v squared may look like a big fraction. And then I take the square root of all that, and then it gives me partial. These are all partial derivatives. And then I just pretty much here from here plug and chug. Okay? So I'm going to make some room for myself or to write all of these down, because I actually kind of forgot what they were. Let's see if I can't just copy this. No. Anyway, let's just write it down. And the arguments are actually all the same. And a lot of things are going to cancel out. See, for this one, still that, it's the only thing different is the 4.7 squared. And it's still sine of the same argument. So this actually simplifies everything quite a bit. you notice that first there's negatives, but they all cancel out to 1. That all cancels out to 1 as well. And so basically you're left behind with just square root of 1.2 squared 4.7 squared. So that's just simply, and it's squared too. So it's just really 1.2 over 4.7, and 1.2 should be over time, this is rads per second, and this is rads per meter. Okay, so even the rad cancels out, and you get a nice unit. Let me write that in blue of 3.9. Oops, I think I have this reversed. Meters per second. So I'm sorry, I made a mistake here. So this is actually reversed. Like, how is it going to get something bigger than 1? So this is actually the 4.7. This is the 1.2. 4.7, 1.2. Okay? Because this was the second derivative with respect to time, and this is the second derivative with respect to position. Okay, so this would give you units of radians per second squared, and this would give you radians squared per meter squared, which should give you units of the end of meters per second. Okay, I apologize for my mistake there, but hopefully that made sense. The units should always make sense, and the magnitude should always make sense towards the end. So even as I say that, I realize this is not yet complete. It's just simply 4.7 divided by 1.2, and then there you can get your wave speed. Okay, enjoy.